My name is Brianna, so feel free to get my attention if you need to. So I'm going to begin with just a review of one of the things that Meninder just talked about, and that's where soil comes from. So these are 4 different minerals, and if you ever took a geology course, you've probably seen things like this, or been to a museum, anything like that. But this is 4 different types of minerals. We've got quartz, feldspar, basalt, and then sandstone. And each of these different types of minerals could serve as parent material for soils. So given the right conditions, the correct temperature, the right amount of water, these could potentially be broken down into soils. And you can probably imagine, just based on the way that they look, that the soils that come from each of them are probably going to look different as well. So maybe the sandstone soil would look red. The basalt soil would probably look black. But in addition to just the way that these soils would look, they also have different chemical properties because of the parent material that they came from. So we just did a soil textural analysis activity where we determined the percentage of sand, silt, and clay in a soil. And now I'm going to look a little bit more closely about the differences between sand and silt and clay, because there are differences in those 3 different textural fractions, and they have a big impact on soil chemistry. So these are electron microscope images of sand, silt, and clay, and I know that they're a little bit small in your handouts, but the scale here is given, and the scale is different for each image. So this first image has a scale of 100 micrometers. Is this small little area right here? That's 100 micrometers. Here, 100 micrometers is this longer line here. So you can tell just by the size of the scale bar itself that these silt particles are significantly smaller than the sand particles are. And then finally we get down to the clay, and you probably can't even see it, but this scale bar right here is quite small, and that's 10 micrometers. So these clay particles are several orders of magnitude smaller than the silt, and the silt are significantly smaller than the sand. And again, this is what's demonstrated here in this little activity that you guys all got. You can see the difference between the sand, again, which is the green ping pong balls, the silt, which is the blue beads, and the clay, which is the white beads. And this is to scale. So if you were to take these sizes and blow them up just so that you could see with your eyes, this is to scale. But one thing you probably also notice is the way that these different fractions look. So sand particles, everybody knows what sand looks like. But you probably have never seen silt before, just because it's too small to really see with your eye. But they look quite similar to these sand particles, just slightly smaller. The one that is very distinct from the other 2 are the clay particles. And the clay particles look like sheets. Unlike the sand and silt, which are individual particles that aren't really interacting with one another, clay particles occur in sheets, and they are typically held together quite strongly to one another. Because of the chemical structure of these different particles, sand particles typically don't have a strong charge like surrounding the outside of the particle. However, clay particles do have a significant charge. So clay particles are typically negatively charged in most of the northern hemisphere. There are some areas in for example, the Amazon rainforest in Brazil where soils are actually the opposite and they're positively charged. It's very interesting to work with those soils. But for today, soils are negatively charged. We're just going to assume that all the way through. Yes?
Is that why you specifically made them like staticky?
No, that's just because the balls are really tiny. So if the the things are staticky. They just need some humidity. So if you like exhale, is a little weird. I didn't do this to any of your bottles. But if you exhale into it, it puts enough moisture in there that they won't be staticky anymore. So again, sand particles, no charge. Clay particles, strongly negatively charged. And because clay particles are so much smaller, even in just a very small area, there are many, many, many negatively charged sites in clays. And this relates to what is called the soil's cation exchange capacity, or CEC. And this is a measure of the total number of negatively charged surfaces within the soil that are able to adsorb or capture cations. So cations are positively charged ions. So a soil with a high cation exchange capacity will be able to capture and store a large number of cations and more than a soil with a low cation exchange capacity. And something that's important to know, both clay, so I've been talking about clay quite a bit, it has a negative charge, but organic matter also has quite a few negatively charged sites and is able to absorb cations just like clay. Yes?
Why do the clay particles stick together so much if they're both negatively charged?
So there are specific crystalline structures inside clay particles where some have a positive charge, some have a negative charge, some have a positive charge, and they like pancake themselves together so that on the outside they're all negatively charged.
But within, they got
yes, there are things called octahedral layers and tetrahedral layers, and it's very chemistry-like, and I didn't want to get into that. But yes, there are reasons why, and there are even different types of clay that are attracted to one another differently and which have different charges because of them. So this is just a little animation. So we've got clay particles here in the middle, and you see the little bars indicate negative charges. So here we have a clay particle surrounded by, they're positively charged, so they are cations. Very good. And then on the other side we have a clay particle surrounded by negatively charged anions. Awesome. So this little animation just shows what happens. So those cations are attracted to the soil, and the anions are repulsed from the soil particles. So negatively charged things do not stay in the soil. They are pushed through the soil, where positively charged ions are attracted to the soil surface.
So does this mean that heavy clay soils are often lacking in nitrogen for plants because they are not being held?
They can be, yes. So, good catch. Nitrate is one of the ions that I included here that is repulsed by the soil. So nitrate does not stay in soils very long, but nitrogen can also be found in other forms, like ammonia, that are positively charged. And those can stay in the soil. But microbes like to break that down. So if you do have nitrate in your soil, it does flush through the soil very quickly. And this is actually one of the reasons. So fertilizer, when you apply nitrogen fertilizer, if it's converted to nitrate, because nitrate is negatively charged, it moves through the soil very quickly. And this is how we get nitrate groundwater contamination, because it goes straight down to the groundwater. All right, so to demonstrate this, we have an activity that's called soil as a filter. And this will demonstrate how soils filter water both physically, so they remove physical impurities from contaminated water or dirty water, and then we'll also demonstrate how soils filter certain chemicals out of water. So this addresses the structure of matter and chemical reactions, next generation science standards. And then we have our list of materials. So for this activity, I'm going to have you guys work in groups of 2 or 3. I wouldn't get any bigger than 3 because it's going to be a little tight. But the things that you're going to need for this activity are in your bucket. So you should each have some 5-ounce Dixie cups and some 3-ounce Dixie cups. We are going to need 4 of each. So you guys can, split it up amongst themselves, or one person can use all of your cups. I've already mixed up Kool-Aid for you. You each have some on your table, so you don't need to worry about that. This is for you to take home. Of course.
Caffeine-free.
And then everyone, you will need 1 toothpick per set of cups. So the way this is going to work is the small cups are going to sit on the bottom. The bigger cups are going to sit inside them. The bigger cups are going to act as a filter. So the big cup's going to sit here, and you need 1 toothpick per pair of cups, just to make sure that we don't create a vacuum. So you should all have all of these materials in your buckets. The large cups poke holes in the bottom so that water can go through. As many as you feel. So once you have poked the holes, take your smaller cup for each pair. Just sit the toothpick right inside the cup, and then put the bigger cup right on top of it. So again, this is just to make sure that when we put water in here, it's going to flow. And if we don't have that separation, it's going to create a vacuum. So do that for all 4 sets of your cup. Yeah, small cup, toothpick, big cup. So now we are going to use the soil that came with your buckets. So you should have a Ziploc bag with lots of different types of soil. There's one in there that's sand, and it's clearly sand, and you'll be able to tell exactly which one it is. I think it's the only one that's not labeled. You can ask your students, what is a filter? What does a filter do? And then you can ask, do you think that soil can be a filter? It's probably not something most people have ever thought of. So you can just sort of stimulate their thinking. And then finally, do they think all soils filter in the same way? For the first 5-ounce cup, that's the big one that's on top. We've got holes in it already, so fill it half full of sand. So what you can do, you can just use the cup itself as a scoop and scoop some of it into the cup. And then once you've got the sand in the cup, go ahead and put it back inside the smaller cup. Pour some dirty water through your sand. We are going to move on to the Kool-Aid. So now with your second cup, your second big cup, go ahead and fill that full of sand as well. And then you can use the Kool-Aid at your table to carefully pour your own Kool-Aid. Now that we've done sort of one replicate, we're going to do the same thing again with our final 2 cups, except that you're going to fill the bottom of the cup with sand and then put the natural soil from this morning that we collected outside, put that on top. And put a good amount of it on there. You want about the same amount of sand and soil. Their filtrate was darker with the natural soil, which means it probably picked up some of the soil and pulled it through with it. Your results might vary because, remember, we said those cation exchange capacity sites, those can get filled. So if you have more purple food coloring than you have exchange sites on the soil, if you added too much water, your filtrate can still come out purple. So it really is variable depending on how much soil you have, how much of the liquid you add, and if you want to be more precise about all of this to make sure that your results come out exactly as you expect, You might need to do some tinkering with whatever soil you're going to use. So what are the take-home messages here? So soil is a natural filter, and it filters all of the water, most of the water, that goes into lakes and rivers. So it physically removes grass and rocks and other things from moving through the soil, but it also filters out chemicals in a similar fashion as what happened with the grape Kool-Aid. And these same techniques are used to purify wastewater that comes from homes and cities, everywhere really. If you have a septic system, these are the principles that are used to filter your wastewater. And finally, a healthy soil is important for drinking water. All the water on the earth goes through the soil at some point in its life. But a lot of the time, there's a biological component in those sand filters. Sometimes there is, sometimes there isn't. But there's, for example, for drinking water, there's something called a bio-sand filter, where you actually allow beneficial bacteria and algae to begin to grow in that filter. So they have some impact on the water quality. Also, one of the major things is you want to slow that flow rate down. Like our flow rate now was very fast. It was moving through this sand really quickly. So if you can slow that down a little bit and use finer sand, that will improve things quite a bit. Yes?
Is there any soil that will filter lead?
That will what?
Filter lead?
Filter lead. That is a question.
We have a lead expert
There we
here.
go. James is going to take it away.
So soil that has a lot of phosphorus in it. So, urban soils are just loaded with phosphorus because people add phosphorus fertilizer. So lead will bind with phosphorus, kind of like a caboose hooking onto an engine, and it forms a relatively insoluble mineral called pyromorphite. So that's one of the way to what we call sequester lead in the soil.
To fertilize a lot, you care about the lead.
Well, that's the double-edged sword, because in Chicago, when people fertilize and you get a heavy rain, or they decide to water their lawn, and if it's like my neighborhood, one of my neighbors likes to basically water the sidewalk until they're standing puddles, and then it goes over the curb and it goes down the storm drain, and it goes down to the world's largest wastewater treatment plant in Stickney, Illinois, where on a day like today they're treating over 1 billion gallons of combined raw sewage. And so it can lead to eutrophication. So that's, but you don't probably need to add a lot of phosphorus to your soil anyway.
Well, does that release the lead when plants are growing? Or does it stay bound?
No, it depends. The area around the root, called the rhizosphere, if it is acidified enough, then yes, the lead can become detached and be taken up in the roots. And so root plants, like carrots,
Yep.
the thinking now is that you should peel the skins, because the outer skin may contain higher concentrations of lead. Same with tomatoes.
If your soil isn't particularly acidic, is it more likely to stay bound up?
Yes, so if you have an alkaline soil, and a lot of these soils are high calcareous soils because of the limestone base. 100 feet below us here at DePaul, you will hit solid limestone bedrock or dolomite. So yes, we have neutral to alkaline soils.
Does when you're talking about your neighbor who waters so much and everything, so does the lead that's in these soils get into the water that we're drinking?
Well, lead, attaches to clay particles. What Rana was talking about, cation exchange, yes, and it can be carried. And the thing about lead in Chicago that is totally overlooked is all of the focus is on lead in drinking water, because we have these lead service lines, which can leach. And the drinking water plant, the one down by Navy Pier, you know, they add phosphates, they add alum to precipitate stuff out, and they add phosphates to boost up the pH and make it alkaline. And what happens is when that water gets pumped out through the water mains and then into your lead service line, it forms this coating on the inside that's supposed to prevent lead from leaching. Problem is when they dig up your city's main, they have to disconnect your service line. That jostles that kind of protective crust on the inside of the pipe, and then you've got fresh lead exposed, and that can leach out. That's a really good question about how much lead is actually being transported down the sewage infrastructure to the plant that has soil particles that have lead on it, and I don't have an answer for that. But overall, nobody focuses on lead in soil enough in the city of Chicago. Sarah was an author on a recent paper done by Dr. Andrew Margonaut at the University of Illinois, which was a really broad-based study where they collected samples in all these different neighborhoods. But we don't focus on lead in soil enough in major cities.
Another important part of soil chemistry is knowing the soil pH. So the soil's pH determines, probably most importantly, the nutrients that are available to plants within that soil. So you can test your soil's pH to know which plants will grow best in your soil. And if you're a gardener, you probably know some of this already. And then you can also compare the soil pH with other substances. So some of you might have seen me walking around. I put some things on some of your tables, and we will do this in just a minute. So inside your buckets, there are these two little envelopes, and they should have been, I think, with your cups. But the inside are some pH indicator strips, and there are two different scales. So one of them is the full pH range, so 0 to 14, and the other is 5 to 9. But you can actually use these little indicator strips to test your soil pH. So we have here today to test, of course, we have our soil. So there's an activity, a full printout of the activity right after the one we were just looking at. It's called Soil pH. It's on page 41. And it has all of the steps here. So under part 2, it says prepare a sample. It says you use a 1-to-1 ratio of soil and water. So if you use, and it can be by volume, it doesn't have to be by mass. If you use half a cup of soil, add half a cup of water, stir them up, and then allow it to settle for like 10 to 15 minutes so that the soil, just like our little jar over there, so the soil settles down to the bottom and there's that supernatant on top, that liquid on top without the soil. And then you want to dip the indicator strip with the yellow side into that supernatant, and then use the indicator diagram here to determine the pH of your given soil. And you can do this right now if you have some of your soil left over, your natural soil. So here we have a diagram that shows the pH, and this scale goes from 4 to 10. And here we have several nutrients that are essential for plant growth. Some of them you probably know, like the big 3, nitrogen, phosphorus, potassium. Plants have to have these things to grow. But also sulfur, calcium, magnesium, iron, manganese, boron, copper, and zinc, and then molybdenum also. And you can see the width of each of these little strips varies depending on pH, and that is an indication of how available each of these nutrients is at a given pH. So for example, if your pH is 5, copper and zinc, this is the widest area of this bar, so copper and zinc are highly available at a pH of 5, but phosphorus, not so much. So if your plant needs a lot of phosphorus and your soil pH is 5, maybe you need to do something, maybe you need to add some phosphorus, or maybe you need to try some remediation to bring that soil pH back up to a pH where there's more phosphorus that's available to the plant. There are 16 essential nutrients for plants, and they are, if I can read this, carbon, hydrogen, oxygen, phosphorus, potassium, nitrogen, silicon, calcium, iron, magnesium, boron, manganese, chloride, copper, zinc, and molybdenum. And I know that's a lot, and it's probably a lot for any student to remember, but the mnemonic device will help. So the sentence that this mnemonic device creates is, Chopkin's Cafe is managed by mine close cousin Mo. And yes, it's not grammatically correct, but it can help you remember these 16 plant nutrients, and you can see it's written out in slide 27 on page 35. If any of you are gardeners, you probably know this. So for example, azaleas like a soil pH that's really quite low, and I can't get that chart back up there because the computer locked up on me. But the reason azaleas like a low soil pH is because there's a lot of aluminum that's available at a low pH, and they like aluminum. So they really thrive in a soil with a low pH. If you guys have seen also hydrangeas, you know, sometimes they're pink, sometimes they're blue, sometimes they're purple. That has to do with the soil pH. And so I believe, if I remember correctly, the element that they like and that causes that color difference is copper, if I remember correctly.